I'll be talking about maybe a very simple question about that can you, in a laboratory, can you create, with the help of matter, whether the matter can be in two different places, spatially separated, and if matter couples to your gravity, as you just heard a couple of minutes ago, where the geometry could also be in two different places simultaneously. Yeah. And technical words, these are called this picture. So this picture shows that if you have a matter and you're in a quantum superposition in two different space-times, technical word many times people talk about is like Schrodinger's cat or macroscopic quantum superposition. So that's the question which I would ask, and you would see that what are the repercussions. And plan of my talk is to talk a little bit about the foundations of quantum mechanics, and then macroscopic quantum superposition. I'll talk about two experiments. If time permits me, I'll talk about the second experiment a bit more, but maybe I'll focus on this first one. Is to really perform an experiment to test whether, first of all, whether it's possible to do this kind of setup, whether you take a matter, create a superposition, and if so, what can you learn about the nature of space-time? Whether the space-time behaves classically or space-time has some quantum properties. So that's the kind of question which both the experiments actually are asking for. But in short, the acronym for this experiment is QGEM. It's a real experiment, quantum gravity use entanglement of masses. And I'll explain the entire QGEM during this talk. I will briefly mention you what are the challenges we have, because these are very demanding experiments, extremely hard experiments. If we can ever do this first experiment, that will be the most precise experiment human being would ever do on Earth. And why particularly Earth, we'll come back to that. And maybe, if I'm lucky, I might be able to see through this experiment in my lifetime. And this is even harder experiment. And I will tell you what it's done. And of course, like every experiment in physics, although we are digging, asking questions about the very foundations of space-time, they have immense applications in real world. And I'll briefly mention about them as well. Okay, so let's start with very beginning. From the beginning, very simple, space-time and gravity. I think most of you have heard already about concept of gravity from our school days, actually. I mean, you see that if you ask, gravity is one of the oldest topic of physics we have come across. The days of Newton, Isaac Newton. And then, of course, there are many, Galileo was perhaps one of the few pioneers who started doing the experiment with gravity. So it's indeed very fascinating. And of course, the subject has grown from its very nascent stages to now what we are talking about, along with other interactions of nature. Now, what do I mean with that is that, as you have heard already, the electromagnetic interactions, the charges, they also repel or attract depending on the nature. Then there's a weak interaction, the neutrinos, they follow weak interactions. Then you have very strong QCD interactions, the quarks, for instance, they're held by gluons and nuclei. In hydrogen atom, the nucleus itself has 3 quarks, protons. And similarly, So the question is, if we know these interactions, we have actually understood it painstakingly. I mean, various experiments from Fermilab in America to LHC in Europe, CERN. We have understood these interactions. to a large degree. But what we have not understood so far is the nature of gravity. That's why two bodies attract towards each other. What's the microscopic origin behind that? At least for electromagnetic, I know that is a photon. You quantize your electron as well as photons in quantum electrodynamics, and through this interaction, you can understand the electromagnetic why even two charged particles attract or repel, the dipoles attract or repel, and so on and so forth. Even higher order multipoles, you can actually understand from quantizing both photons and your matter. Matter is yes, electron positive. But in the case of gravity, we have not been able to, although we have the machinery, but we still don't know what the machinery which we use is the right one or not. And the reason is we don't have an experiment yet. And so my way of taking is that as long as you don't have an experiment, it becomes a debate. To a large extent, it becomes a philosophical debate, because what actually crosses the Rubicon River is the experiment. Unless until you have an experiment, you really do not know what's the truth. And even if you do an experiment, there are various levels of interpretation you can entertain. But let's go with the simplest interpretation and try to understand what we understand, even if we have done the experiment. So as far as these electromagnetic interactions, UCD and weak interactions are concerned, we have kind of like settled the debate. Yeah. But for gravity, since we still don't have the kind of experiment which you would love to have, it leads to various debate, various discussions. So okay, so that's the fact about gravity. Now, yes, please.
On this diagram of the graviton, right? Could graviton be colored? I mean, is there any experimental evidence against it?
And actually, I think of course there's a theory paper, as you know, by Britain, and even before Britain there was this.
I don't know. Sorry, explain.
Yeah. So I think if I recall the theorem, I think it says that as long as you have local interactions and you follow the gauge invariance and everything, all the properties, then and the locality, the interactions are local, then you cannot have, for instance, composite Spin-2. I mean, sure. So that theorem.
No, but I'm asking color. I mean, in a sense, what I'm asking. Well, I mean, can it be non-trivial group, non-abelian or something?
No, it is actually. So in some sense, I mean, of course, as you know very well yourself, that the general theory of relativity, if you try to be, if you take, first of all, you perturb the space-time gently, and then if you try to quantize that, and it has the same non-abelian nature, comes out like QCD. So that we know. Now, whether you have a colored gluons, whether you have colored gravitons, that I think, I don't know, I have not seen any, but maybe if you know, please let me know. I mean, that's an interesting thought.
I mean, what I'm saying is, if there is more than one, can I just subsume this in the Newton constant, and which is, I can say this is the constant of Z, which contains the number of gravitons, right?
Mm-hmm. No, I mean, yeah, in principle, one can think, but I do not know whether one can be consistent or not.
Because even classically, they will be inconsistent. Because once you go on the polynomial level, then you can count.
Yeah, exactly. So the classically, maybe would be inconsistent. So the theorem which I was mentioning, perhaps, cannot be composite. I mean, you have heard about Spin-2. Now you can think about Spin-2. Can I think about constructing Spin-2 with 2 Spin-1 or even 4 Spin-halves and things, so on and so forth? But that's not possible. Now there is some loophole. Now you can circumvent those loopholes, and then you can. And one example would be string theory, because string theory is inherently non-local. So there are some loopholes where you can entertain, you can think about some compositions, but not in general local interactions. Okay, but it was proven by, I think, Weinberg and Witten. But even before that, I think people knew it in Harvard. I'm trying to remember the famous name from Harvard. What's his name?
Georgia.
In Georgia, I know the other one. He passed away quite early. Anyway, so he knew he had Coleman and Mandula. So it's kind of like Coleman, Mandula, and then Weinberg and Witten kind of like banking all the arguments there. Okay, good. So what we know a little bit about gravity, I can tell you, and I think Tomislav knows a lot more, many aspects which he has actually worked on himself. So as far as the gravity, as far as I mean, the experiment is concerned, or day to day, like we are dealing with solar system physics or anything where the perturbations are very, very tiny, we can actually treat this as an effective field theory. And what does it mean by effective field theory is that it's a low energy approximations. At low energies, you can do some, expansion, gradient expansion, for instance, like in Taylor series, very simple way of thinking. And as long as we are working with a very low energy regime, you should be able to ask, based on the symmetry, what other terms can you add, and what are their predictions, and so on and so forth. So people have done this many. I mean, it's not me. It has been done from the days of 50s, 1950s, mid 50s. Many people, many scholars have contributed to it. And actually, like the way you quantize photons, you can also quantize the spin-2 fields, spin-2 graviton. And actually, the person who actually quantized a photon, Suraj and Gupta, he actually had a paper also for quantizing gravity. And then many famous people like Feynman and Kibble, Weinberg, Desert, many people have actually quantized. So what does that mean is that you take a flat space-time, you perturb that flat space-time, and you quantize that degree of freedom. But keep in mind, being spin-2, there are more degrees of freedom than just photons to begin with. But then you have to make sure that you quantize only the physical degrees of freedom. There are also non-physical degrees of freedom, which you actually remove it by massaging the states and so on and so forth. So it's a bit complicated, but people have done it since the days of 50s. And based on this, actually, this approach of treating gravity as an effective field theory, it was reincarnated by Donahue, and Byrne is one of the person who has and his groups have actually managed to use this technique to even predict the black hole coalescence, which people see in LIGO, Virgo, and they can make very good predictions beyond Newtonian, so post-Newtonian corrections. So they use this kind of just quantum field theory, certain techniques to predict higher order terms. And if you want to take a look in a very simple way of treating these things, I have written a few papers. Partly I had to write it. It's not because they were not known in the literature, because here I was working between two different fields. One was experimentalist and one was theorist. So sometimes you need a bridge to the two different areas. So I had to write it, some papers. They themselves not very revolutionary, but they kind of like highlight some of the basics behind what people had already done in the context of an experiment. So that's the very simple aspect about spin-2 graviton. Now, also we know many times people will say that why bother with quantizing gravity? It has ultraviolet divergences in the sense that you cannot predict as you go higher and higher energies. Like QED, you can predict the coupling, predict the interaction strength, and so on and so forth. In the case of gravity, things blow up in the ultraviolet, in the extreme high energies. So, but that statement is also partly true, I would say, because there exists a theory of gravity in 4 dimensions, which is known as quadratic curvature gravity. Means there are, so you have heard that there is R, Ricci scalar, in Einstein-Hilbert term. But if you add Ricci scalar square, then R mu nu, which is the Riemann square, and then the Y C mu lambda sigma, or the R mu lambda sigma square. So combination of those terms actually give you quadratic curvature gravity, which is known as Stirner's gravity. And Kelly Still was actually one of my teachers in Imperial. Unfortunately, he passed away last year. But he showed that this class of theory of gravity in 4 dimensions is perfectly renormalizable, exactly like your QED. However, it has some issues. The issues are with there are some new degrees of freedom which come in, and those new degrees of freedom actually breaks the unitarity. So there is some discussion, but it's a very hot topic. Many people work on this. Some people say that yes, it's good to have. I mean, it's okay to play with these new degrees of freedom, and some people try to even modify quantum mechanics, because the new degrees of freedom, how should they act on your state and so on and so forth. They try to modify the Hilbert space to accommodate these new degrees of freedom. So it is a very hot topic of research now, and many people have many ideas here. Now, so having said these two, now based on these two, I mean, these are kind of like the bottom up. Yeah. So we know that there exists a theory, which is string theory, which is almost 30 years old now. As old as perhaps the quadratic curvature gravity, or even slightly longer history it has. But it doesn't have ultraviolet divergences. In some sense, it's ultraviolet free. But what it does with that, string theory, what it does is that the interactions are no longer point-like interactions. It gives us the concept of locality. It becomes the interactions at the level of your worldsheet becomes non-local, because strings are 1 + 1D objects rather than, and the interactions are also in 1 + 1D objects, cannot happen just on a point, but in a smeared 1 + 1 dimensions. So that's the story of string theory. And then the last approach people actually follow, and I think many of our colleagues in this country, they follow, especially from Nijmegen, that this is called loop quantum gravity or Poisson set theory. There are various approaches of understanding quantum gravity, where you do not, so the basic idea is that you again put some cutoff, not with the hard cutoff, but assume that you're quantizing some areas. The area becomes a fundamental object instead of like position and momenta and so on and so forth. So corresponding to area, you can also think about, in a very loose sense, you can imagine the conjugate of area also. And that way they try to quantize it. However, one of the challenges they face here is that there's no infrared. So there's no good limit in infrared, because that they have not been able to show, but maybe it's a pure technical difficulty and maybe people can overcome it. Smart people are working in this area. So why do we emphasize on that? Because the reason is that whenever you build new theory, whatever new theory you want to build, you have to make sure that in the low energy limit, you should recover exactly what you have seen. Like Einstein's gravity did not throw away Newton's theory of gravity. It accommodated it. Yeah. At low energies, it actually recovered Newton's theory of gravity.
Listen to where.
So similarly, electromagnetism, when the quantum field theory, you in the low energy limit, you recover. You show that why the Coulomb law is valid. It didn't throw away the Coulomb's laws. So in the same way, whatever new theory you build, you have to make sure that in low energies, you recover what you have known so far. Yeah. And this is the kind of that challenge which the last frontier faces. And we don't know how to understand, how to explain that completely, but the effort is going on. People are working in the state. However, having said so, these are I would say these are the primary ways of dealing with gravity in the quantum domain. But still, experimentally, we still lack the evidence of this gravity. Yeah? So this is what I will be talking about. So let me start with something very, very simple. So what I want to emphasize here is that if you treat matter and gravity, space-time, on equal footing. What I mean by equal footing is that if you try to quantize your matter, then if you try to quantize your space-time, and when I say quantizing the space-time, what I mean is that I'm taking a very smooth limit. So my metric is your flat space-time eta mu nu. Now there are some small ripples on that eta mu nu, which I define as h mu nu, and I try to quantize that h mu nu. You see, so that's the only thing which I'm doing. Even I'm staying at the very lowest order. Yeah, and within that limit. So the thing is that if you treat matter and geometry equals to metric, g mu nu, if you treat them on equal footing, it's a very simple example of quantum gravity. Because you see that when you try to imagine, now you try to create a macroscopic superposition. You see? So when I say macroscopic superposition, then think about like an interferometer. You have heard about interferometers like in LIGO, which uses the interferometer with photons. Those who are coming from physics background, they might have even experiments with Fabry-Perot experiments, Fabry-Perot with photons. And so these are interferometers or Mazumdar interferometer. You take photons, you split the photon and take two different paths, and then you look for interference pattern. So these kind of experiments. So if you do with matter, and that matter could also be photons, but for the time being, let's take a massive field, massive particle, M. You can show that as you create a superposition of matter, you are also creating a superposition of geometry. See? And the proof is actually very simple. It's not very hard to see. You can see it in a very simple way. So there is a particular set of coordinate systems known as Fermi normal coordinate systems after the famous physicist Fermi, Enrico Fermi. And so what he does is that, suppose there's a massive particle following some geodesy. If you place yourself in that particle's coordinate system, how the space-time would look like. So that's all about. And in that particular, so a freely falling observer, suppose if I'm freely falling, how would I see in my own vicinity, what's the space-time? So that's the kind of coordinate system it is, and it's known as Fermi normal coordinates. And in Fermi normal coordinates, you can show with a little bit of mass, just few mass, and assuming that only you are playing with the two components, one space and one time. See, just two dimensions. Don't go into even higher dimensions. So this is a picture where time actually goes, if you start the superposition from here, so time goes upward, and this x is a position, and shows that you are creating this superposition. And in this picture, what you can show, a very simple equation, the 0, 0 component of your metric is given by the second derivative of this h mu nu. So just 1, because I'm playing with 0, 1 component times x squared. And this quantity, which is written here, is actually related to your Riemann curvature, which is the 0, 1, 0, 1, 0, 1, 0, 1, the only combination because I'm dealing with t and x, 0 and 1 component. So if you demand that your x, so what is x? X could be imagine your harmonic oscillator. Imagine this is your harmonic oscillator. And now this harmonic oscillator is following through the geodesy. Now you can quantize this harmonic oscillator. Yeah. So as you quantize, you know how to quantize harmonic oscillator. You can quantize the position, momentum. You use the commutation relationship, and then you recast it in terms of A and A Dagger creation and annihilation operators, and so on and so forth. So if you quantize this, the harmonic oscillator, actually that you are quantizing the position and momentum. So here, imagine that the particle is falling very, very slowly, extremely slowly, so that you forget even the momentum terms also. You can add those momentum terms, but you just take into position. So the position will be an operator.
So you are neglecting the gravity.
No, right now the information of gravity will be there actually.
But it's not one. It's not a potential.
No, it's not a potential. It's not a potential, but I mean the information. I'm just giving a very toy model example of 0, 1. You can do it 0, 1, 0, 2, 0, 3, but just to simplify. So the information of the metric is here. That's what I'm saying. So if you quantize this, harmonic oscillator, which is quantizing x, putting x as an operator, then immediately your metric has to be also an operator. It has to be an operator valued entity, and so is your this contribution. So all that to make it compatible, to make it consistent, all the three quantities have to be an operator valued entity. Now, what are operator value entity? It's like your position is an operator, momentum is an operator, or angular momentum is an operator, which acts on a vacuum to give you discrete eigenvalues. So that's what we say.
So you're saying that both H and X is an operator.
Yeah. Then if you say that X is an operator, then to make it consistent, you also have to, if you want to treat gravity as quantum.
But in second quantization, I mean, H is an operator, X is just a coordinate.
Yeah, you're correct. And what I mean in a very loose sense that the H mu. So here, if I go for all three, then if I quantize this X, and if I want to treat gravity as a quantum entity, I'm bound to also quantize H mu to be consistent. It's just a consistency argument, nothing more than that. Yeah. But here, some philosophers actually discuss a lot, and that's why I thought that to present this argument. And and the argument comes from the philosophers is that how do I know whether space-time, this H g mu or H mu, which I have spoken, is actually quantum? And that's a valid question to ask. It could be just classical. And to be honest, even as a physicist, we treat it many times to solve many of our problems, where we treat gravity as a classical, and that is known as semi-classical treatment. Yeah. The famous, for instance, famous calculation due to Hawking is actually based on semi-classical treatment of gravity, where we showed that the information gets lost from a black hole. So here you can see again, now, very interesting observation, very simple, because yeah, you can see that I'm playing with just 2 dimensions. So I have the same picture, space and time. Now, if I, as I said in the first slide, if I treat X to be my operator valued entity, this quantity R01, which is the Riemann tensor, is also an operator valued entity. Mass is constant. I take C is the velocity of light, and so is my H11 hat, and so is my Hamiltonian, which is my operator valued entity. So it has to act on some vacuum to give me some meaningful answer. Now here in this example, just with this example, you can show that all the interactions are quantum. They are acting on the individual vacuums. X, the position of a harmonic oscillator, is acting on the harmonic oscillator. R0101 will act on the space-time, because the states which you create from the space-time vacuum. So this will generate you, because you have X, R0101, it will actually generate a tripartite entanglement between matter and the gravity. So gravity here, by saying gravity. So matter and graviton will give you a very interesting tripartite entanglement. And that you can show, and we have shown it in one of our papers. But on the same side, and similar way, some people actually argue that what happens if so you see on the left-hand side is just an interaction. As an observer, you will say, I just measured this interaction, left-hand side is the Hamiltonian, and that I'm happy with that. But how do I know that this one is for quantum? My space-time would still be classical. Yeah. I just quantize my harmonic oscillator. I can still say that, okay, I can make it compatible. There's something on your right-hand side is operator valued entity. On the left-hand side is operator valued entity. But this entity is purely classical. If someone doesn't believe in gravity being quantum, can say this and can challenge us. So, okay, so this is classical. But in this case, in this example, it becomes like a semi-classical theory, because curvature is purely classical, matter is quantum, harmonic oscillator. You will see that there is no entanglement builds up between gravity and matter. So very simple example, like in 1 + 1 dimensions, you can show, you can demonstrate that if you treat gravity as purely semi-classical theory, classical theory, and you just quantize the matter part, there is no entanglement built up between matter and gravity sector. Now, what is entanglement? So let's come to that question. So in a simple language, so you see that so far we have been talking about mostly space-time, gravity. Now I'm switching the pace a little bit, and this part has, as such, there's nothing to do with gravity, because it's a very generic discussion. Entanglement and entropy are very generic to quantum systems. from condensed matter, quantum mechanics, quantum optics, every field it has benefited. It's a very powerful tool to actually understand the behavior, the correlations, non-trivial correlation which it provides as compared to classical systems. So quantum system and classical systems behave slightly differently, and that difference arises in entanglement. And what entanglement does is it actually measures this correlation. And a simple way to understand, so suppose you have got two systems, and these are quantum systems. So A and B are quantum systems. Now suppose the wave functions can be written as a product state. So you can separate. So I can say that my left hand and right hand are completely independent. Yeah, I can separate them all together. So these states are known as product states. In product states, suppose A has a qubit, spin up and down. This is a quantum system. Yeah. Now that qubit, you can build correlation between just the qubit, build correlation of the B's qubit, but the qubits of A and B, they don't talk to each other. But the moment you allow to interact, so when I say interact, I mean quantum interaction, not just classical interaction like what I'm doing in my hand, but real quantum interaction, then you build up an entangled state. And what does that entangled state does is that it will break this property. You no longer can separate them together. Now, this has given a nightmare in quantum mechanics, and it has a huge history from the days of Niels Bohr and Einstein, and they had a huge amount of discussion in early 20s and 30s, and that led to spooky at distance due to Einstein, Podolsky, and Rosen. Okay. So it has a huge history behind that. It's not that Einstein did not understand quantum mechanics; he understood perfectly well. He just wanted to brought a way of argue that what is perhaps the missing link, or still we don't understand many aspects of it. But now, thankfully, the entanglement issue. There is an experiment. Now, a few years ago, there was three people got the Nobel Prize just to prove this that quantum mechanics is actually is a valid way of at least interpreting the experiments. So far, whatever we have done. But of course, quantum mechanics itself has huge problem with the measurement. So my working principle here is that measurement is a postulate of quantum mechanics. I don't want to address the measurement problem in this talk because that's a completely separate talk. I don't want to entertain that discussion now. But maybe during in the pub you can talk about the measurement problem of quantum mechanics. Anyway, so that's the story about entanglement state and product state. Now, very interesting thing happens is that you can actually, Volman, who have to define this entanglement entropy, you can do some bit of math and you can show the density matrix. You can trace out one of the either B or A, you can trace out and you can define an entanglement entropy. But barring the mass, what is interesting here, so for a quantum system, so suppose you take us, let's imagine that we are all qubits in this room, and it's a closed universe, a closed system. Yeah, we don't talk to outside. So total entropy is 0 for this system. But if I divide it, say I call it one half of this room and the other half of this room, in a classical way, you will say entropy should always increase. But that doesn't happen in quantum.
So you're not saying that the symbol SA in the second equation is equal to the symbol SA in the first equation.
Here, it's a quantum. Because
no, I know, but
either you
the symbol SA in that equation is not the same as SA in the equation below, right?
No, this is different. So here, what I'm saying is that if these are quantum system, then the total entropy will be 0.
Yeah,
because
but these symbols are different.
Not really, no.
If they were the same, then that would imply SA is equal to SB is equal to 0.
But I mean, for the bipartite system, it is true. For a bipartite system. Not for all parts. I mean, just for if you take two systems, A and B, then the entropy of A and entropy of B, they are same.
But they're not equal to 0.
No, then, sorry. Yeah, they are not exactly. That's the point which I'm making. That in a classical sense, we say that they will increase.
No, but
if you say, yeah, so in order to show this, what I'm saying is,
think that these symbols are equal, then I'll conclude that SA is equal to SB is equal to
No,
0.
so this statement is for closed system.
Sure.
I'm putting an extra
So
boundary.
that means you're assigning a different meaning to
Exactly.
SA.
Yeah. So if I impose that the system is closed, then the total entropy is 0. But classically, it would never be. So in that sense, the classical entropy is very different from this entanglement. So that's the statement I want. So in this sense, the entanglement or entanglement entropy is a bona fide quantum entropy. You cannot find a classical analog to this entropy. Okay, so the question is, how do you generate entanglement? Now, it's a very hot topic, as I said, that if you take any theory, theorists love to compute entanglement entropy. You give them condensed matter system or QED, QCD, string theory, or any kind of system in various backgrounds. People like to compute entanglement entropy. Usually, it's called the vacuum entanglement entropy. Physically, you can think about the vacuum is really not vacuum. It is doing something very interesting. There are fluctuations going on. You are creating pair of particles, annihilating. So there's something always going on in the vacuum. And that non-triviality will generate you an entanglement entropy for a vacuum. Typically, it goes like the area law plus some corrections depending on the nature of the problem. Sometimes you get some corrections at higher energy, or if you cite the vacuum, you get corrections. But typically, if you are looking at this entropy of a vacuum, that they go like area. Now, if you, that's something very interesting, but people have shown, many people, I think even in this room, people have shown, and also Susskind and other people have also shown that, very interesting that if you take this vacuum, and after all, you know that every excitation, we talk about quanta, particle, but these are also the excitations of your vacuum. Now, if you suppose you excite these quanta and you scatter them through the vacuum, you can actually exchange the entanglement. So that's something which is very interesting. The point of the vacuum, you can exchange the entanglement between particles. These particles, like call them Alice and Bob, you can actually transfer that entanglement. And what does the transference of the entanglement means? Because the particle itself is, when I say electron and photon, you see everything is in a vacuum. So, but there is always an interaction between electron and photon. I cannot separate that interaction. You see, they are not separable systems. They always have the interaction. And that interaction leads to transference of entanglement from one sector to another sector. You can think about it. So, you can think about in the context of gravity, if you just bounce two masses through the vacuum, the Alice and Bob, they will actually now get entangled. That's the idea. And there's another theorem, actually completely different theorem. Actually, to be honest, I didn't know myself before 2017, when I started working with this with experimentalists and quantum information people. I got to know about this theorem, which was known by Bennett, and Bennett is actually considered to be the father figure of quantum computing. Way back in mid-90s, Bennett and many other colleagues, and after all, there are many papers have been written in this context. The statement is very simple. So the statement is called LOCC. So LOCC, what it stands for, what it means. So LOCC means that you have got, suppose, Alice and Bob. Let's say that Alice is doing some quantum experiment, Bob is doing some quantum experiment. Yeah. But if the outcome of Alice's experiment, let's say it's measuring spin up and spin down through some Stern-Gerlach kind of experiment, it notices spin up. If it tells that information to Bob, classically means I just put it down in my piece of paper, give it to Bob. In that context, or in this protocol, Alice and Bob will never get entangled. So that's the theorem. So you can do local operation, means unitary operation at this end, whatever you want to do. You can do the same thing at Bob's end, but as long as you communicate purely via classical channel, you will never entangle these two systems if they were not entangled to begin with. So if they were separable systems, they would remain separable even after this exchange of information. And so this is a very powerful theorem, especially you can, in quantum communication, quantum teleportation, this is the part of the theorem, which is used in deriving or showing many of the statements in quantum information society. However, now you can think about very interesting conundrum. And the conundrum is that at low energies, as I said, no matter what happens at very low energy, you have to, whatever theory you build up, you can build up a very complicated theory, but it doesn't match at low energy, then it means there's something which we don't understand very well. So at low energy, you need to make sure that they are compatible. Now, what you can show, I'm not showing the mass here, but just my statement. Suppose if you take Alice and Bob, and if you write down some interaction between them, you can actually write down very interesting interaction combining their position and momentum. Something like XA, XB, PA, and there are other terms. You can write it down. Now, as a philosopher, you can debate this question that, okay, at low energies, I see only this. And these are quantum entities. These are operator valent entities. So XA and XB, imagine Alice is a quantum oscillator, Bob is a quantum oscillator. I don't have to know anything, what's happening in between, just two harmonic oscillators, you see. At low energies, you can write it down like XA, XB, BA, PA, BB. You will say there is a quantum interaction between Alice and Bob. And you would immediately say, hey, look, there is an entanglement between A and B. Yeah, just by looking at low energies. But the question you have to ask is that how did you derive this at the first instant? You see, so that's the place where the physics hides. Yes, you can get this kind of interactions, you can get this kind of Hamiltonian, and you can even conclude that A and B are now entangled now. But LHC immediately tells me that how this interaction has been mediated. And if I cannot answer that question, I cannot satisfactorily answer my, understand my point that whether A and B are really entangled or not. See. So in some sense, it's very much like I was talking about Fermi, and Fermi has done many work, and he was an excellent theorist, also an excellent experiment. Very few people can do both, actually, in the physics world. But so he came up with this very beautiful discussion of 4 Fermi interactions. Yeah. So if you take just 4 fermions, and these fermions could be your standard model fermions, could be your leptons. So simply think about leptons. So these are 4 Fermi interactions, and you are showing it by block here. And you would say, suppose you didn't know the theory, high energy theory. You just knew as a low energy observer, you knew this theory. And of course, the 4 Fermi interaction generates an interaction, and it will entangle. All the 4 fermions will entangle with each other. It will not be tripartite entanglement, but it's a 4-party entanglement between A, 1, 2, 3, 4, incoming and outgoing fermions. So it will develop an entanglement. But this is a low energy consequence of slightly more complicated diagram, where these two, now you can think about a separate entity, and they are being mediated, their interaction is being mediated by W bosons. W boson is one of the scalars in the standard model in your electroweak interaction, electroweak sector. So same thing can happen also in gravity. Now suppose if I merge these two blobs, it will look like a point interacting like here. Yeah. But then you can ask, what really gave you the interaction, or what really these two particles, why they are actually getting attracted? You can ask the same question for Coulomb, why the two particles are repelled, or why the opposite charged particles get attracted. Then immediately you would see that in the case of Coulomb, there's a photon which has mediated, and in the case of gravity, if you quantize gravity, you would see that there is a virtual excitation which leads to this entanglement.
But so the graviton is massless. The Fermi
yeah, that's the subtlety. Yes, very good. That's absolutely correct. There is some subtlety here. Here, as Tomislav said, that these bosons are massive. We have found it experimentally also the mass of the W and B bosons, but gravitons are so far as we know, from various experiments, from other experiments such as even with LIGO, gravitational waves, so on and so forth, we have a very tight limit on mass, and virtually you can take it to be 0 for all practical purposes. These are massless degree of freedom. So this analogy is not completely in the same sense, but it captures certain aspect.
But there is also Heisenberg Lagrangian, right? Which is F to the fourth.
That's true. That's
And that is kind of effective.
Yeah.
There is a,
Yeah. I didn't want to get into that, but yeah, actually, there's a very beautiful example, which Tomislav mentioned, that even in QED, so QED as a low energy theory, you can take Maxwell's theory as low energy theory, but you can actually, and you can treat it as an effective field theory.
Yeah.
You can go at higher energies, at one loop, you can generate a theory which is called Euler-Heisenberg theory, and it's still very hot topic. Even in LSC, people are looking for signatures for this kind of theories. Also, people believe that when you take a very high intensity laser beam, it can split into electron and positron and just the string pair production, and that might also generate you the Lagrangian, which the prediction of that process can be explained also possibly by this kind of Lagrangian of Euler and Heisenberg. So it's a very, very hot topic, in fact, of research. Yeah. So how am I doing with time? Please, someone tell me, and then I can.
No, you have to the 10, 15.
10, 15 minutes. Okay, I will speed up a little bit after this. Okay, so one thing which I want to show you, and very simple, again, it's a very simple quantum mechanics, first quantum mechanics, not even higher level quantum mechanics. The first, even I teach it in Groningen, this one-page discussion. So let me discuss this very simply. So suppose you take two harmonic oscillators, yeah, A and B, and these are quantum harmonic oscillators. Now, let's go to the occupation number. Let's say that they are in ground state, 0, 0, occupation number. Now, let's say that you have interaction, and that interaction is HAB, and lambda is your bookkeeper's number. So lambda times HAB, you have added an interaction, and as a consequence, what will happen? This initial state will evolve. Yeah, it will evolve to some final state, and final state will be now excited state because you have added an interaction. Then let's say that your occupation number for Alice is small n, for Bob is capital N. Yeah, something's different. So now what you can show, just one line derivation. So that you take the final state, you can actually write it in something which is called product state. Yeah? And as I said, the product states are separable states. So what I have done here, I have just taken A and N, B and N, summation of all possible excitations. I have added them and subtracted them. See, that if you think carefully, they will just simply cancel out. So this part looks like a product state. It means that they are separable. But this part spoils that product state, the behavior of the product state. Now, if this is non-zero, you immediately see that the final state after quantum evolution becomes an entangled state. And you can compute these coefficients, and these coefficients can be found by just the overlap between initial and final, and the energy difference between them. And as long as these are non-zero, you can show that your final state is entangled. Now here, HAV, this interaction could be anything. It could be QED, you can take QCD interaction, weak interaction, phonon in quantum matter system, gravity for the case of quantum gravity, and you can actually show how the higher order states get entangled in this way. And so in some sense, what I wanted to say that any Hamiltonian which you can generate in gravity, if you treat both matter and gravity on equal power, all these terms are your operator valued entities, and even the lowest order terms, higher order terms, and so on and so forth. And you can compute, people compute this. As I said just a couple of minutes ago, Dreeburn and others, many colleagues have actually now found various techniques to compute these kind of contributions, and they are very useful for your coalescing black holes and so on and so forth. Even for LIGO, Virgo, and future Einstein telescopes. Similarly, one more experiment which is very beautiful and which is very important actually. The reason, if you remember, that after Einstein gave the general theory of relativity, first test of theory of relativity was the light bending. And at the same time, actually, there was a very interesting mathematician character from Finnish character, very well-known mathematician called Newstorm. I think his name was Gunnar Newstorm. And he also was thinking about, gravity and space-time, but the philosophy was slightly different. Einstein's philosophy was treating space-time, the basic structure was your tensor. But Newstrom was telling us that at that time that if I had to reproduce just Newton's potential, because again, you need to reproduce Newton's potential, can I do something different? Can I make it simpler? So instead of making curvature based, can I have some scalar exchange? And in Gunnar's theory, it was just a scalar exchange which would give you Newtonian potential. The coupling would be square root of G, scalar interaction mediator which generates you 1 over R potential. But there was a catch, and the catch was this experiment. Because if you remember, if the angle, the deflection angle due to general relativity is 4 GM over R naught. Yeah? R naught is the distance away from the light rays propagating from your center of mass of your system. So here, for example, is a white dwarf. Now, in Newton's theory, it's 2 times GM by R naught. And in that classical theory of Gunnar's, where he could reproduce Newton's potential, this deflection angle was 0. And again, it's very easy to understand because a scalar field, so you see that imagine instead of graviton, if I had a scalar field, you have a matter, you have a photon, a scalar field can couple to your photon through trace because phi is it has no other indices. So phi can only couple to the trace of the energy momentum tensor, phi times t. But the trace of the energy momentum tensor of a photon is 0. So there is no interaction. And as a consequence, there is no reflection in that theory. Despite explaining that there is, Newton's potential, he could explain that well, but he could not explain, his theory could not explain the deflection angle. So that was a very powerful way of showing that, yes, we should construct theories and we should try to see how much we fail, because then only we learn. And that was first example, not only that experiments show that we are successful, but also even theoretically lends some support. And again, you can compute this by one graviton exchange, and it produces exactly the same deflection angle. But now, interestingly, what you can show is that the matter and the photon would get entangled, and they would get entangled through the exchange of this graviton. So again, if one can do this experiment in laboratory, it's a very hard experiment, but it can be done. Now, let me give you in a couple of minutes, 5 minutes, perhaps? Yeah. So in 5 minutes, let me tell you a little bit about the experiment. So how are we imagining to do this experiment? So what we are trying to do is, so we are taking this again, imagine this is your Alice. There are 2 quantum systems, and this is Bob. And these are exactly like your Stern-Gerlach experiment. You might have come across Stern-Gerlach experiment in your school or high school, where what you do is it's a beautiful experiment because that's the first experiment which actually showed us that the electron has spin up and down. Yeah. So if you ask a question about what's the spin, and the way to understand is that you send some ions and you put an inhomogeneous magnetic field, and then what happens is that the spin of an electron of a fermion couples to this external magnetic field, and the spin up and spin down couples differently because of the eigenvalue plus and minus. So there's a differential force between up and down, and you see that here, which was spin superposition, it takes 2 different paths. Yeah. And that's the Stern-Gerlach experiment, because you see by Bohn's rule, you see half of the time spin up and half of the time. If you do many experiments, many repetitions, you will say 50-50 up and 50-50 down. And that was the very first experiment to show that the electron has a spin. So precisely the same experiment, but now we are dealing with gravity. So you need these objects to be slightly more massive. It cannot be electrons, cannot be atoms. It has to be slightly more massive. How massive? And this we'll discuss now. So imagine you have the Stern-Gerlach experiment here, Stern-Gerlach experiment here, and you bring them sufficiently close to each other. Okay, so these are neutral particles. But even if you have a neutral particle, like suppose this is a neutral, there's no net charge, but it has dipoles. It has higher order multipoles. You see, it has induced dipole. Suppose there is a charge here, it can induce a dipole, electric dipole. If there's a magnetic field, it can induce a magnetic dipole. So all these things are there, even in my neutral system. However, there's very interesting fact that electromagnetic interactions can be streamed. You can stream them, but gravity cannot be streamed. So I can create a screen between Alice and Bob to suppress all the interaction between them through electromagnetically, but gravity can still interact and see each other. So we need to do all this kind of setups to do the experiment. But of course, when you bring a screen, it also brings other problems, challenges. You have image problems, image charges, and so on and so forth. But you can control those things. But just to tell you that, yeah, gravity cannot be screened, and you can do such an experiment. So then what you do is that you create, again, it's a space-time diagram. You create a superposition with delta x, just to have the same values. You end the superposition here. So what will happen is that you have created the spin up and spin down. So you create it from here, and you brought it here. So there is interference happening between the spins. Exactly like the photons go through the interference double slit experiment. The same way, imagine that it's going through an interference pattern. And in this interference pattern, you can actually read the spin. How many times you have spin up, spin down, in X direction, Y direction, Z direction, you can read the spin here at the end of the day in the experiment. The same thing you can do for Bob. And then what you do is that you build a correlation between these two systems. And as I said, the entanglement measures the correlation, which is in a quantum entanglement, there's a quantum correlation. And you see how many times you have spin up, how many times you have spin down. If these two systems were not entangled, you would get 50-50. You will get always 50 times spin up, 50 times spin down. But if you start getting 50 times up, 51 times up, and 49 times down, you will start seeing this entanglement. So there's a non-trivial entanglement building up between the two systems. So you can look into the wave function, the evolved wave function, and so you have a spin up interaction, spin down interaction, then you have up down up interaction. So these are the interactions between up down and down up, gives you something called entanglement phase. And you can measure the entanglement phase, and at the lowest order, what it turns out that this entanglement phase is this quantity, and this is the order parameter. G n square divided by h bar, the t is the distance, and delta x is the superposition, delta x by d the whole square. Now you see that you would say that the g is very tiny number, h bar is also very tiny number, but interestingly they come as a ratio. So despite g being small, h bar is small, their ratio comes in, and so there is a Goldilocks zone where if you tweak your masses, your delta x, d, and tau time, you can actually get order 1 entanglement phase. So in 2017 paper when we wrote, we put this number, we quoted this number. So if you would take 10 to minus 14 kilograms, if you create superposition of 100 micron, this distance to be 500 micron, and if you keep this system alive for 1 second, you can generate this entanglement phase to be ordered up.
How many atoms? Is it billion or?
Yes, so the mass 10 to minus 14 kilograms, it means there are roughly 10 to 11, 10 to 12 times the carbon atom, let's say. Right. So right now, so what is the current state of the art? So current state of the art is people have done amazing experiments in Vienna with 10 to minus 21 kilogram objects, virus, even with COVID virus, but the superposition size is very tiny. It's very hard to create a micron superposition. With atoms are being very light. People can create half a meter spatial superposition. And now in Fermilab in America, they're trying to create 1 meter superposition. So very large superposition with atoms. And there are plans even to perform the experiment in space, where you can perhaps even gain more delta x. But that's likely more towards the future.
Question.
Yes.
Is the system 1, can I think of it as a bell pair?
Sorry, Stefan, say again.
System 1, can I think of it as a bell pair?
Yeah. So yeah, system 1 and system 2 both are.
So 2 bell pairs. So the bell state itself is maximally entangled.
Exactly.
And yet you create entanglement with another system, but I thought that's violating the monogamy of entanglement.
Yeah. But sorry, maybe this is, yeah, your statement is correct. But This together is a Bell state. The final state is the Bell state.
And not the individual
Not the
system.
Individually, they are just superposition, like spin up and spin down. But as a whole, if it's maximally entangled, then it's a Bell state. How much time? 2-3 minutes. Okay, very good. So I think I'm pretty much close to ending my talk. So the important thing is that for this experiment is exactly like what Stefan said, that you need to do this correlation. And Bell was the first person actually to build this kind of correlation to falsify whether, whether there are hidden variable theories or whether it's quantum mechanics. So very similar, like Bell's witness. But now this witness is slightly more evolved because Bell in the 1960s. Now there's a huge development in quantum information. And right now, people use something called positive partial transport witness, which can actually find out the entangled states for a bipartite system, because it's a bipartite system, two systems are involved. And people nowadays we use this witness for our experiment, which our colleagues have given. And what happens is that the density matrix of this, what we created from this state you create a density matrix, and if you take this W, this quantity has to be less than 0 to show the entanglement. So in real life, actually, this experiment is extremely hard. We are inching towards that a little bit day by day. We are making some very tiny progress, but what I can tell you a little bit about what it requires to do this kind of experiment. And I think maybe in future, Netherlands can play a very beautiful role in really performing this experiment. So first is the quantum coherence. You have to maintain the quantum coherence of these systems, which I said. You see, it's very interesting. I want to understand the entanglement feature of gravity, due to gravity. But this system, Alice, is already entangled with this environment, electromagnetic interactions, all sorts of interactions. So I need to kind of like purify the state of Alice. Simply, I have to purify the state of Bohr to perform the experiment. You see the entanglement due to gravity. To start with, to begin with, I need to really purify the states, means I need to maintain the quantum coherence. I have to really go for the quantum harmonic oscillator at its lowest value. So I cannot expect very high excitations. I have to go for ground state, holding up the harmonic oscillator. I have to protect it from the vacuum, as I have to isolate it through electromagnetic interactions, pressure, particles. Everything can destroy the coherence of the system. And it requires the pressure, something like, I don't want to quote the number, but I can give you an analogy. It's the same pressure where LHC, our in CERN, performing this experiment, proton-proton collision. So proton-proton collision, where they do this collision, that's a very good vacuum. There was slight misalignment happened because the vacuum was not very stable, and that stability was destabilized by the TGV train, which was passing through from Geneva to Paris. And even that was a slight misalignment. So the vacuum has to be very well protected for these kind of experiments. The objects which I showed you, the temperature has to be around 4 Kelvin and below. And then you have to shield this experiment, because it's a 1 second experiment, and 1 second experiments are very dangerous, 1 to 10 seconds, because if I perform an experiment here in this room, I'm susceptible to something what's happening in Boston. If there is an earthquake happens and tsunami happens in Boston, even my experiment will see that effect. So it's so sensitive. So I need to protect it, and what we are realizing, the best way to protect this experiment for those who are young people is exactly the Einstein telescope. Which will, where they will really build the Einstein telescope in the tunnel.
Sorry, but isn't it better to go to space? No?
Space, yeah. So of course it is better to go to space, but it's very expensive. B, it's a repetition.
Sure.
If something goes wrong, then you lost your experiment.
Yeah.
So here at least you can, something. Of course, there will be something which will go wrong in the experiment, but you can control it on Earth. So that's one. I mean, you don't have to read these values and all. You can ask me if you're interested. But just to tell you that, so Joris one, and again, he was a PhD student in Nijmegen. Now he's in Belgium. So he's in Einstein telescope, and so we collaborated with him to understand that what is the sensitivity and whether this Einstein telescope is really good to host this kind of experiments or not in future. And it turns out that that will be the place to host this kind of experiment. But that means since I'm already over time, I just end the talk by there, it goes on and on for the experiment, but I have given you the gist. But one thing I want to tell you, just 1 second, that these experiments can do many interesting things besides just gravity. First of all, they can be very good test of even standard model. You can test axion, because if you can see graviton may lead to interaction and entanglement, even axion can lead to entanglement. You can test, for instance, the light bending experiment. You can even test something which is way too higher than your LHC can. Very special theories. I mean, these are called massive gravity theory. Some time ago, it was very popular. Brain world theories, where you can have graviton exchange ADS to the bulk and so on and so forth. But I don't want to get into the details. But it has the potential to test physics of 10 raised to 7 GeV, way beyond the LHC scale. And yeah, we can also test the equivalence theorem and so on and so forth. So besides us, other groups have also worked on it. But let me now come to an end. So you see that a very simple question, like whether space-time is classical or quantum. It requires a huge amount of technology from particle physics to condensed matter, because after all, these objects are really condensed matter systems we are dealing with. Material science, we need to understand the material properties of this system, because we want to really go to the ground state. Laser physics, cosmic rays physics, because cosmic rays can actually destroy the coherence of the system, earthquakes and everything. So it's really I would say, very ambitious, highly disruptive, but community effort. So it's not just one group can do it or one lab can do it. Many labs are involved now already, but more the merrier, because it gives the strength, it gives the community to go forward in terms of finance, in terms of everything. So please, if you are interested, any of you young people are interested, contact me through my email, and I'm happy to address your question. Thank you very much.